Hello, I'm Ed Pegg Jr., and welcome to another episode of Mathematical Games, a series in the spirit of Martin Gardner's Mathematical Games columns from Scientific American. For 25 years, he did monthly columns for the magazine, and it was a very influential set of columns. Uh, they were later compiled into 15 books. However, um, with computers, many of the items that he talked about in his columns are improvable if you apply a computer program to them, because we have about 1 trillion times more power available than people in Martin Gardner's time had. So, I'll be showing some of the new items that have come out just in the past week, in addition to some other things. So we, of course, have many demonstrations devoted to polygons and polynomials. They're highly useful objects in mathematics, and I'll be covering a few of the items mentioned in these screens. But first, one of Martin Gardner's columns, he talks about ways of constructing a polygon with folding. And this item over here, folding a strip of paper to make a pentagon, this was one of the first things that fascinated me in Martin Gardner's columns. I think I was maybe 6, and I did have access to strips of paper, and I folded a pentagon, and I found that absolutely fascinating. It wasn't shown in school that you could do this, but in one of these columns, it showed how you can do some interesting things in mathematics. So I really liked this one example of constructing a pentagon from a strip of paper, and that sort of led to many other fascinations with mathematics. We have a demonstration showing you can go beyond that. For example, you can fold a heptagon with a strip of paper. So one item that he talked about was packing one shape into another of the same shape. So here's where Martin Gardner talked about packing squares. And this is a difficult problem. There are several square packing solutions that are somewhat famous in memes. And I think the 19 case has been improved since then. So one similar problem is packing hexagons into a larger hexagon, and the a classic case is 13 hexagons fit in a hexagon in a particular way, and until recently, the best known solution for packing 12 hexagons was just to remove one of them, and that was the best known solution for packing 12 hexagons, and that was considered settled until last week, when Alpha Evolve at Google gave these two solutions for packing 11 and 12 hexagons, which were completely unexpected, but they had Alpha Evolve look at all sorts of problems, and the AI found this new solution, which is better than the previous one. The previous best solution for 12 unit hexagons required a regular hexagon of side length 4. But with this packing, you can get it down to 3.942. So they didn't give a exact solution, so I figured I would solve that. The exact solution is this, which is a root of this order 10 polynomial. I mentioned I'd be talking about polygons and polynomials. So here's an example of a polynomial, which is a solution for a particular polygon packing problem. So I went ahead and made a diagram of it. Let's see if I can make this font smaller. So here's the exact solution. I used first, if you take a point in the center here, I noticed that this was rotationally symmetric. So basically, I put the center of this triangle at the origin, 0, 0, and I dropped down a value j to get the point for this hexagon. And I noticed there was an offset between these hexagons, and I just called that k. I fed those into Mathematica and then calculated what these 3 points would be. And I noticed that for this to be a hexagon, this distance had to equal this distance. So I solved for what are the parameters for this distance equaling that distance in terms of j, and that gave me a term for what j would be in terms of k, and then I fed that equation into minimize, and it gave this solution. And also it gave me the values for j and k, and then I just finished up with everything else. This is the intersection point for here. So this is a method of using polynomials and polygons to solve this problem put out by Alpha Evolve. And I wanted to welcome everyone here. If you have any questions, feel free to post them in the chat. Another item he talked about is semi-regular tessellations. And I found these fascinating. I became quite interested in tessellations, and on Facebook, I have a tessellation group, which is popular. Recently went over 100,000 subscribers. A way of looking at tessellations is you can take, say, squares, and they can be modified with a hinged dissection. Here's a way of doing it with triangles. And quite a few of these semi-regular tessellations come out from these. Some of these dissections are used by NASA for spacecraft for unfolding solar panel arrays. And one of them was recently used for solving another square packing problem. I'll be showing that eventually. So another item he talked about quite a bit is geometric dissections. Here's an example for cutting 3 squares into a larger square. And I gave a talk about this in episode 8. So I don't want to revisit all of those, but if you go to episode 8, you'll be able to see the full talk I gave. This link, of course, will be in the talk when it's posted on community.wolfram.com after this talk. Another item that came up is bracing the square. You have a number of toothpicks and you want to brace a square so that it can't be moved. You want a rigid graph, basically, with all unit lengths. And it was an open question at the time, how do you brace a square? And they came up with several nice ways of bracing a square with this. These are incorrect solutions over here. When I read this at age 10 or so, I had no idea that I would eventually be one of the people known for solving a bracing problem. So here's the square solutions. We have them in graph data. These are ways of, here's a square here. Here's a minimal way of bracing it. And here's some of the methods that were shown in the column. All of these vertices, if you look at them, have constructible roots. So these are all drawable with ruler and compass. Here's the braced pentagon here, slightly more complicated. You can barely see it here under all the vertices right over it, but this one is a bit more clear. This is a rigid graph for how to brace the pentagon. And here are the vertices. They get more complicated with order 4 and order 16 vertices. So this is an order 16 polynomial you needed for this one. They get a little bit more complicated. For the braced heptagon, I came up with this graph here. And this is one I came up with 20 years ago. It's been in graph data for a long time. I'm not sure how many versions you can go back and find it. Maybe version 7 or 8 in Mathematica. But this was in there for a long time. And then a decade later, I was looking at this graph I came up with, and I wondered, is this a rigid graph? And it turns out it is. In fact, it's so rigid that you can take any two connected vertices and completely wipe them out, just rip them out, and all the edges connected to those two connected vertices, for example, this here, and no matter which two connected vertices you pick and rip out, it's still a rigid graph. So this is somewhat a super rigid graph here. And it's the minimal solution for bracing the heptagon. A nice, elegant solution with a heptagon on the outside, a 2-star heptagon, one end where it skips one vertex each time, and then a skips 2 vertices each time on the inner. So it's both heptagon stars in a heptagon, all fitting together perfectly with unit length edges. All these edges have length exactly 1. And the polynomials, the polynomial roots, order 6 and 12 for these vertices. So I talked about geometric constructions. One item to construct is the pentagon. So if we start out with this diagram here where we've constructed an eye basically, so draw a circle, then pick a point, then we draw this arc here, we find this intersection point, and we finish off with a pentagon. This is the geometric construction of the pentagon. And here's some rules here for how to do it. So these are our classic constructions, and it was wondered for over 1,000 years what other polygons could be constructed. So if you restrict the problem, it's still possible to construct many of these polygons. For example, here's a way to find the center of a circle mentioned in Martin's column. And one person who is quite interested in this is something I found while I was reading up on from this column, was one person was Gaspard Monge, who was a friend of Napoleon. He was pretty much a best friend of Napoleon. And one item it's back here. One item he did was the Monge center of a tetrahedron, which we have a function for, the Monge program. I did not know that he was a friend of Napoleon until I worked in this column, because I'd forgotten about this section. Doing points on a line is another thing that involves polygons quite a bit. Here are solutions for the orchard problem, where say you want to have 10 points and you want 12 lines of 3 points, and these are solutions. This is a a strange solution here, 11 points making 16 lines. It's one of 4 known sporadic solutions which have slightly more lines than is predicted by a particular equation. Do I have the? These are the 4 known sporadic solutions, and I talk about these in my column, Cultivating New Solutions for the Orchard Planning Problem. Terence Tao took a look at the problem, and he proved that there is only a finite number of exceptions to the formula for the maximal number of points and maximal number of lines you can get from a certain number of points. And these are the 4 known exceptions. In my column here, I show 1/5 solution, which also does 16 points with 37 lines that was unknown. So one solution for 4 points, there isn't a good solution known for n points and the number of 4-point lines you can make. That's still an unsolved problem. And one sample of that was this solution here was unsolved up until, I think, 8 years ago, somewhat recent. It was, so this is 28 lines on 22 points. And this, if you take out the middle point here, that was known for 30 years. But it wasn't until 8 years ago someone had the idea of, what happens if you put a point at the center? Doesn't that give a better solution for this problem? And it turns out it did. And I'm one of many people who knew about this Grunbaum-Rigby solution, and I never thought of adding a point at the center. And so far, I haven't found any mathematicians who did beat the solution that was posted on a Chinese site near Christmas. I think 6, 7, 8 years ago. So that was a surprise, and it's still unsolved how many lines of 4 you can get from more points beyond this. But some of these solutions might be very simple that just weren't known. So these points here, here's a polynomial here that can be used for creating heptagons. And here's a plot of this cubic, x to the third minus 7x minus 7. So I like this one because I can remember it. It's just sevens. It's a cubic, so I know it's an x third. And I know it's just 7x and 7. And it's a heptagon, which is 7-sided. We can find the roots of this. So I'd like to use this root here because it's positive, and it has a number field discriminant of 49 or 7 squared. If you're looking at a geometric problem and you get a algebraic root, the first thing I will do is I'll look at the number field discriminant to see what algebraic space I'm in. And often it's a low number corresponding with a particular cubic. For example, I believe 23 is the plastic constant. So if we look at the coordinates of this heptagon solution here, here are the order 6 polynomials and order 3 polynomials. If we square them and we look at the polynomial space, I mentioned this one here is x to the third minus 7x minus 7. If we look at the square root space or algebraic number space, everything converts to nice integers. So these are all of these points, which are sextics and cubics. So there's a paradigm in mathematics and physics that if you're not sure of the answer, the first things to try are 0, 1, and squaring, or the square root. Well, it turns out if you're looking in geometry problems and you've got polynomials, one of the first things to try, if things aren't working nicely, is to try squaring the roots that you get. And often that makes everything work well. So these are, again, the sporadic solutions that come out of this. Another construction that was tried, they weren't able to solve the heptagon with compass and ruler. And another one they couldn't solve was the nonagon, or nine-sided polygon. Here are the points. To construct the nonagon, you would need to trisect a 60-degree angle. And for hundreds of years, they thought that was possible until it was finally proven that you couldn't do that. So here's, it turns out for the nonagon, which is 9 sides, the cubic for the nonagon is x to the third equals 9x plus 9. So this is the other cubic equation I'm able to remember, because it's a nonagon, you just need 9s. And I like using this root. So for the algebraic space of the nonagon, you just use this root and everything becomes nice rational points for the construction of the nonagon. And it's possible, if you fold paper with origami, you can do cubics. And it turns out here's a solution for constructing the nonagon. And all you need to do first is to construct the points square root of 3, 1, and minus square root of 3, minus 1. And then you just fold the points onto the axes, and you get the folds that make a nonagon. And I'll get to that a little bit later. Euler's identity also involves polygons, because it gives a method for converting the exponential function into sine and cosine. So here's an example of using Euler's formula for constructing various angles. Oops. Need to enable dynamic here. Hopefully it'll let me do that. Good. So with enough terms, we might need to scale out to see it. With enough terms, it spirals in on a particular value. Sometimes it's easier to spiral in than others. Oops, scaled too much. So these are taking successive terms in the expansion of the exponential function, which is a series of sine and cosines, and you get these spiral lines. In 1796, Gauss stunned everybody as a teenager when he showed that the 17gon was constructible. You just needed to come up with this particular constructible root for for pi over 2 pi over 17. And it was Wansel who proved that any regular polygon is constructible if it's a power of 2 or a distinct Fermat prime, which are 2 to the n plus 1. There's only 5 Fermat primes known so far. Gauss also introduced cyclotomic polynomials as another way of constructing polygons. So these polynomials here, which are factors of x to the n minus 1, these are the cyclotomic polynomials. Now you might notice that all of these polynomials, the maximal there's some negatives and some positive, but all of the coefficients for everything are just 1. There's no values above 1, and you might think that that keeps happening. Well, it turns out for, let's take a look here at 105. For here, we get the first 2. So it's not the case that all cyclotomic polynomials have only coefficients of 0, 1, and -1. You can also get higher values. You just need to go to very large exponents in order for that to start happening. This was, it was considered for a while that cyclotomic polynomials would never have indices above 1 until somebody tried 105. So there's 3 related sets of polynomials: the Pisot polynomials, Salem polynomials, and the cyclotomic polynomials. And I have a demonstration which compares them. So with a cyclotomic polynomial, you can get points on the unit circle if you look at the roots of that polynomial. So these are all examples of particular cyclotomic polynomials, and it's not quite a polygon, it skips points. But if you have all of the different roots of a particular power of n, x to the n -1, then you'll get all the points, but you can also factor out and only get a subset of points. Some of these here. They get different patterns. And here's an example of a Pisot polynomial where the roots in complex space are inside the unit circle and there's one on the outside. And let's see if I can find some others here. Another Pisot polynomial. And here's a Salem polynomial. This one has almost all the roots on the unit circle, one inside and one outside. So these are the different polynomials relating to the unit circle on which polygons are often drawn. It's still unsolved exactly how the Salem polynomials work, whether there's any other solutions where the maximum value is less than 2. This is a line for 2 here. It's unknown how small this particular root can be for a Salem polynomial. One other way for constructing polynomials is what's called Chebyshev polynomials. And you can get those from looking at fractions of pi in fractions of this value here. So when you do this simplification, you get these polynomials. For a pi over 5, you get this polynomial. For 7, you get these two. If you do pi over 17, you get this polynomial. These polynomials were studied by Chebyshev, and now they're called Chebyshev polynomials of the second kind. Here's a plot of some of them. And these roots happen to coincide with the positions of the x coordinate for these, or no, for the y coordinates of these polynomials. And when they're plotted, they make these interesting patterns. And I believe in many cases, the intersection points are orthogonal to each other. So this is a interesting set of polynomials which relate to polygons found by Chebyshev. Now, I talked about origami earlier, and one of the items in origami is the 7 Fujita-Hattori axioms. You can fold a line through 2 points. You can fold a point onto another point, and those are equivalent to a line and a perpendicular bisector. You can also fold a line onto another line, which is equivalent to an angle bisector. And you can fold a point perpendicular to a line, which is a line through a point perpendicular to a line. A more complicated one is to fold a point onto a line, passing the crease through another point. So for example, if you have a square sheet of paper, you can fold it in half first. So there's a crease line showing the 2 halves of the piece of paper. And then you can make a fold through one corner so that the neighboring quarter will be on the crease. And if you do that twice, you'll get an equilateral triangle. And that's one way you can construct the points of an equilateral triangle. Now the 6th one here, you can fold a point onto a line and another point onto another line. This is equivalent to finding the common tangent to 2 parabolas. So here's an example here. We have this point here, 0, 1, and this point here, -1, -1/2, and we want to fold these 2 points onto the x and y axis. So if we use this fold, that will take this red point and put it to this green point, and this red point and put it to this green point. So this fold here is a Beloch fold, and it was found in 1936 by Beloch, and now it's called the Beloch fold. It turns out if you construct these 2 points, 0, 1, and -1, -1/2, you can construct one of the folds of a heptagon. And this basically, you just need these 2 points, the x and y axis, and you just need to figure out this fold to get these points onto the x and y axis. Similarly, we can construct the points square root of 3, 1, and minus square root of 3, -1. And one fold is this line here, which takes this point and folds it onto the y-axis, and this point here folds it onto the x-axis. So that is one of 9 folds for the nonagon. This fold here will fold the red point to the green point here, and folds this red point to the green point here. That's another fold for the nonagon. A third fold is this crease here, which takes this red point and folds it to here, and this red point folds it to here. So those are 3 of the folds for the nonagon. We can start out with the cyan lines by folding an equilateral triangle using the trick I mentioned to fold a corner onto the center crease so that it goes through another corner of the piece of paper. That will give the starting lines for the equilateral triangle. And then if we build the opposing points, minus square root of 3, 1, and square root of 3, -1 over here, those give, and those are parts of the hexagon construction if we do the opposing of the blue cyan lines. With those 2 points, we do the opposite of what we did with these 2 points, and that gives the light gray folds here. and you get a nonagon folded out of that. I did not know that it was this easy to do the origami construction until I looked into the Beloch fold. And there's a function for it now in the Wolfram function site. We can also fold the cube root of 2. All we need is the points -2, 2, and -4, 1. We fold those onto the x and y axis, and we get this line where a run of 1 corresponds with a rise of the cube root of 2. So all you need is -2, 2, and -4, 1, and you can construct the cube root of 2. We can also fold the plastic constant with just the points -1, 2, and -2, 0. We just fold this line here to put this red point on the x-axis and this point on the y-axis, and we've constructed a run of 1 and a rise of the plastic constant. So I found this fascinating. All of these cubics that were sought after in antiquity, and all you need in origami is a set of simple points and a single fold, and you get these things like the cube root of 2 for the duplication of the cube problem. There's also various tricks you can do with polygons if you give all of them an edge length of 2. So here's one example. We have a n-gon where the edges have length 2. If we draw the perpendicular bisector and then take a look at all of the corresponding lines across and then square these lengths, the total of these lengths, for example, 0.46, 3, 3.87, 1.65, if you add those together, you get they total to the number of sides of the polygon. So these values here total to 9. And that works for any polygon so long as you have all the edges have length 2. So for example, the decagon, 1 plus 3 plus 4 plus 3 plus 1, the total, basically I've squared all of these lengths. You total those together, you get 12. You total these together for the 13-gon, you get 13. So I found that's a fascinating property of polygons where you just square these different lengths and you get the value you started with for the number of sides. And this works for any regular polygon. For example, here's the 20-gon here. These added together sum up to 20. But that's not the only thing you can do with polygons if the edge length is 2. If you draw the annulus, so you have a hexagon here with a, oops, what happened here? No, it's not letting me close this now. So you have a hexagon here with a side length of 2, and you draw the inner circle and you draw the outer circle for an annulus. It turns out that those two together, this green disc annulus here, has an area of pi. And the same with if you do a pentagon. If all the lengths are side 2 and you draw the inner and outer circle, the area between them has an area of pi. Same with the square. Turns out the green area here is equal to pi, which is the same as the red circle. Also works for the triangle and the nonagon. In fact, for any n-gon, if you draw the inner and outer circles and the edge length is 2, the annulus, the green ring, will have an area of pi. So that's another weird thing you can do with polygons if all the edge lengths are 2. For polygon triangulations, if you have a polygon inscribed in a circle, a cyclic polygon, it turns out that if you triangulate it and then you sum the radii of the inscribed circles for the triangles, it's always the same. The total radius for all of these is the same no matter how you triangulate the polygon. Here's another example here. No matter how you triangulate it, you don't need to use a regular polygon for this. If it's any cyclic polygon where the points are anywhere on the circle, if all the triangulations and the total radii of the circles inside, if they're the same, it's a cyclic polygon, and if it's a cyclic polygon, it'll always be the same. So that is one way to check whether a given polygon is cyclic. You just do that triangulation several times, and if they are the same for the if they're always the same for the polygon, it is a cyclic polygon. It's an if and only if relationship. The number of triangulations is given by this formula. It's the Catalan numbers, which is one of the things Gardner talked about in one of his columns. There's 5 triangulations for a pentagon, 14 for a hexagon, and so on here. And I found it fascinating that this is something that was figured out by Japanese mathematicians hundreds of years ago. One thing you can look at is where diagonals will cross. So here's an example for the nonagon. Here's all the intersection points of diagonals for the nonagon. You get all these various points. Most of the intersections here, there's 324 intersection points listed here. Most of those intersection points use order 6 polynomials, as shown by the 6 here. We can take a look at, say, one of these here. Here's the polynomial for this first point here. If we wanted to convert these to get something more convenient, we could try using trigonometry. Sometimes they will simplify this to a nice multiple, nice division of pi. For example, these points here. However, more frequently, it's the polynomials here. This is kind of a bogus polynomial. We tried an approximation, but it turns out this is just an approximation. It's not an exact value. So things like this order 25 polynomial, this is no good. These aren't real exact values. With barycentrics, we can get everything down to cubics, as shown here, if we wanted to represent these points in a nice way. However, if we use square root space, this here is the root of the 9 cubic minus 9 minus 9x plus x to the third, the 9 cubic. If we use square root space, everything turns into nice integers. So, and that applies to all the intersection points. So I like using the squaring method when I'm looking at algebraic values of vertices in geometry. It's a nice way of simplifying everything. And I'm hoping to come up with a square root space set of functions so that if you just know the function, you can get the intersection points and things like that easily without using a lot of higher order math involved with the intersection points of sextics and cubics and things like that. I'm hoping there's a way of simplifying that using this integer representation. One thing I looked at recently is local graphs. Here's an example of a local graph. The non-Cayley transitive graph. This is in graph data. And we didn't have a nice embedding for this, so I figured I could make one. And here's an example. I managed to solve it. So we have the central point here, and it's adjacent to these points on the outside. So and this works for any point. If you take any point, the points next to it make a 9 cycle. That's what a local graph is. And when I played around with it, I figured out that you can take the central point and the nonagon, and then the other 18 points would make 2 more nonagons. And with this particular arrangement here of various nonagons with particular algebraic roots, everything looks nice. So the next item I was asked to look at was the Fricke-Macbeath graph, which is locally equal to the 7 cycle or heptagon. And there's a edge list for this, and it was based on this problem here on Stack Exchange. So I wondered whether I could make the graph look good, because there was no known good representation for the graph. So first I optimized the edge list so that the graph distance matrix looked good. These black squares over here on the diagonal, that means that the distance to this point is 5 from this vertex, and every vertex has another vertex which is 5 away, and that's the maximal distance for the graph. So here's the edge list. Now let's see, I should have used 72 there. So let's use 72 here. And it looks very messy. And this is sort of the best that was known for the graph, that it was a messy graph because it's every vertex had order 7. But I figured I could pull something nice out of it. They did know that if you had half the graph, you could get this nice local structure. So here's half the graph here, and it has a lot of symmetry to it. But how can you do both halves of the graph at the same time? It turns out if you look at the other half of the graph, it looks identical to this. This really nice structure, it looks somewhat different if you try it with just half the graph, but I figured I could make it look much nicer, so I'm using heptagons and certain heptagons with particular roots to make it just look perfect. And then I put everything together. So here's the full graph. You can kind of see in blue here and brown, you can sort of see this graph, but it's not exactly the same. It wasn't too hard to use polygons and particular values to get a nice representation. So this is completely new here. I figured I could make the graph look nice using the properties of polynomials and polygons, and I was right. And that's what I had. I'll be glad to answer any questions if anybody has any. Any questions? I should probably return to the alpha evolve. Yeah, I solved this morning. So any questions? All right, I'll close that here. Many thanks for coming to my talk.